Thank you, everyone. Welcome. Thank you for being here today. And if you see my first slide, if you can have a brief think about what geometric theorems or results you teach your students, and how do you justify, motivate, or prove these theorems with your students. So I'll be speaking about a surprising and fruitful theorem, and my name is Daniel Wolfe-Root. I teach at Hutchison's Grammar School in Glasgow. And if you want to contact me or follow up with any questions, you can email me at this address right here. So maybe you thought about some geometric theorems. Some that are important to me are angles in a semicircle, Taylor's theorem, the theorem of Pythagoras, the sine and cosine rules, and the sine and cosine angle sum identities. Now, if your list was much larger than mine, or you think the trigonometry doesn't belong here, then I'm going to be connecting these ideas by drawing upon other geometry, including the properties of isosceles triangles and right-angled triangles, properties of circles, and similarity. But I want to look at these four rectangle sets of content first. So the first three are covered in National 5, mathematics, and the fourth in higher. And for some of our students, they may see these four geometric theorems or sets of theorems in 4 different years of their mathematical journey. And so what I'd like to do today is show how we can connect that mathematical journey, or show how that mathematics is connected by a simple and often overlooked theorem, the Inscribed angle theorem. I'd like to argue that this is a fruitful theorem because it yields proofs of these 4 sets of theorems. And in addition, one can deduce Ptolemy's theorem from the Inscribed angle theorem. Now, Ptolemy's theorem is also a surprising and fruitful theorem, I think. It's one not typically taught in the high school curriculum, but only high school mathematics is required to understand its statement and its proof. And so I'd like to share that today as well. So the structure of my talk will be, I will introduce and prove the Inscribed angle theorem. I will show how we can deduce Taylor's theorem about angles in a semicircle from the Inscribed angle theorem. And together, I'll put them together to prove the sine rule, or an extended version of the sine rule, which is really lovely. Then we'll go off on a tangent to a circle and discuss, state, introduce, and prove Ptolemy's theorem. Out of that, we'll pop one of the simplest proofs of the theorem of Pythagoras, which I think you'll be delighted by. Although I should say that Chris Pritchard presented this morning another simple and lovely proof. So maybe mine isn't quite the simplest, but it's a simple and surprising proof. We'll put several of these ideas together to deduce a trig identity, and then I'll explain why having one trig identity is sufficient to deducing 4, all the sine and cosine angle and sum identities, and then talk about also how we can deduce the cosine rule from Ptolemy's theorem. So this is the structure of my talk. And at the end, I'd like to talk a little bit about instructional suggestions about the Inscribed angle theorem, because it's responsible for such a big and deep web of mathematical knowledge and understanding. So what is the Inscribed angle theorem? Like all of the mathematics that we teach our students, it is the answer to a question. It's a question that people from all over the world for thousands of years have asked. And it's a question that our students can ask as well, or be exposed to before learning the answer to that question. And it's the question, what is the relationship between an inscribed angle of a circle and its corresponding arc? Here I have, in order to ask this question, I need to know what I mean by an inscribed angle and a corresponding arc. So the terms I'm using are angle CAT is an inscribed angle. That is an angle whose vertex is a point of the circle, and its two sides are chords of the circle. This is a circle with center O, and arc CT is the corresponding arc, or sometimes called the subtended arc or the intercepted arc for this inscribed angle. Now, the question arises what I mean by the measure of an arc. I'm not talking about the length of an arc. And actually, if you look at my inscribed angle, I've drawn it as a green arc. In fact, what is an angle but a fraction of a rotation? And what is an arc but a fraction of a rotation? So to formalize what I mean, I want you to observe that the number of arcs CT that form a complete rotation of the circle is the same as the number of central angles COT that form a complete rotation. And that leads to the following definition of arc measure. So the measure of an arc is the measure of the central angle of the circle that intercepts that arc. So when I say the measure of arc CT, what I mean is the measure of central angle COT by definition. So my original question about the relationship between the inscribed angle and its corresponding arc can be rephrased as a question, what's the relationship between the inscribed angle and the central angle? And just so you notice, I have angle CAT as my inscribed angle and angle COT as my central angle, and a kot is a Russian word for a male cat. You might have been surprised why I mentioned so much trigonometry on the opening slide, the sine and cosine rules, and the sine and cosine angle sum identities. You might not think of those as geometry, but actually in my SMC paper, I talk about the fundamental problem of trigonometry and how it's really the sine function in trigonometry that connects the central angle of the circle to the corresponding chord. And you can see here that we have a central angle, an intercepted arc, and we can form also a corresponding inscribed angle. So that's why this theorem relates to trigonometry. That's where the trig comes in. I was delighted to see Chris Pritchard's talk mention of the 47th proposition of the first book of Euclid's Elements. The inscribed angle theorem is actually the 20th proposition of the third book of Euclid's Elements, and it states that the measure of a circle's inscribed angle is half the measure of its corresponding arc. And here's my 1952 Heath translation of Euclid, and this is the corresponding page. So how do we prove this theorem? First, we're going to consider inscribed angle CAT with center O. Then we're going to form the corresponding central angle COT. And really, the proof will show that the inscribed angle is half the measure of the central angle. And then by the definition I gave, it's half the measure of the arc. First, we form diameter through the vertex A, AS. And then that breaks the inscribed angle up into two angles whose measures are X and Y, respectively. Note that we have two isosceles triangles, AOC, that's a good representative, and AOT. They're isosceles because AO, OC, and OT are all radii of the circle. And therefore, since we have isosceles triangles, we have congruent base angles. And so the angles at C and T are also X and Y. Now, there's a theorem called the exterior angle theorem, which says that an exterior angle, like COS, is equal to the sum of the two remote interior angles of the triangle. So that would be X plus X. If you're not familiar with that theorem, then one way to think about it is that angle AOC is the supplement of the sum of X plus X in order to make the 180 degrees to form the interior angle measure sum of the triangle, but it's also the supplement of the exterior angle COS, the angle COS has the same supplement as x plus x and therefore must be equal to x plus x, or 2x. And the same argument holds for the triangle on the right. Take away the diameter and we have that the inscribed angle measure is x plus y, and the central angle measure is 2x plus 2y, twice the inscribed angle measure, and by definition that's the measure of the corresponding arc. A really nice application of this theorem is the pentagram. This is a picture I took from the entry hall at El Cerrito High School in the San Francisco Bay Area, where I taught for my first 9 years of my career. And I would bring students out here and ask them, what is the sum of the measures of the 5 angles in the star pentagon? And star pentagon, according to Michael Serra, is actually a term. And so I mean these 5 angles. And I would ask my students to go out and figure this out. And they would work away, and they would often come up with the right result. But invariably, it would be because they had assumed that the blue pentagon was a regular pentagon. So what if it isn't? How can we make this work for all such figures? Well, if you notice, each arc of the circle has a corresponding inscribed angle. So the one I drew up here has this inscribed angle, and at the risk of getting this a bit messy, this arc here has this inscribed angle, and I can go all the way around the circle, filling it up with 5 arcs, each corresponding, I'm sorry, I said central angle, I think, but I meant inscribed angle, with one of the 5 inscribed angles. By the theorem I just gave, each inscribed angle is half the measure of its arc. The circle's full arc is 360 degrees. And so the sum of these 5 angle measures is 180 degrees. A lovely result for all star pentagons based on the inscribed angle theorem. Okay, so I've described the inscribed angle theorem, stated it and proved it, and now I'll use it to deduce one of the cornerstones of geometry in our curriculum, Taylor's theorem, about angles in a semicircle. Now, a corollary in mathematics is a result that follows almost immediately, or possibly immediately, from another theorem. And Taylor's theorem is just a special case of the inscribed angle theorem. It's a corollary. It says that an angle inscribed in a semicircle is a right angle. Now, I think this is an astonishing theorem. And when I work with students for the first time and I ask them, what's the measure of angle DOG with center O, although O is stylized here, typically they don't know the answer. And they're not convinced that angle DAG has the same measure. I mean, there's a lot of things that are variant about the situation when we vary the position of the vertex of our inscribed angle. For example, the angle at G and the angle at D, the side, the 2 of the 3 side lengths, at least 2, we don't know the third yet. No, I guess the third is a diameter, and the area of the triangle. So it's not clear that the measure of the inscribed angle is really invariant of the position of the vertex. And so students might agree that the angle DZG and DAG are congruent, but typically they don't believe that all of these angles are. And when I work with students who do know the result and I ask them, why is this true? How do you know? Typically they don't know. So I think this is a lovely theorem to spend more time with students at the beginning. So why is Taylor's theorem true? Well, each of these inscribed angles intercepts arc GD, which is a semicircle. Its corresponding central angle is half a rotation, a straight angle, 180 degrees. So each of these angles is half the measure of 180 degrees, or 90 degrees. Okay, the sine rule. This is, let me describe how I'll start with the sine rule. I'm going to use the inscribed angle theorem, and I'm going to use Taylor's theorem. I'll start with any triangle, triangle ABC, labeled in the canonical way we do for the sine rule, where the angles are capital letters for their measures and their positions, and the opposite sides are denoted for their length by lowercase letters. I'll create or construct the circumcircle that goes through the three vertices. And at that point, I would have trouble finding the sine of one of those angles. So the strategy is to create an angle whose sine I know how to find. And I can do that by forming a diameter through one of the vertices of my triangle, say through vertex A. And since I have a diameter, by Taylor's theorem, I can create a right angle, DCA. And by the inscribed angle theorem, since angle ADC intercepts arc AC, as does angle ABC, it means that two angles that intercept the same arc must both be half the measure of the same thing and therefore congruent. So the strategy is to find the sine of D because it's in a right-angled triangle. So Taylor's theorem plus the inscribed angle theorem show that the sine of B is the same as the sine of D. And so that's B divided by the diameter, which I've denoted by 2r because I have a D already. So the sine of B is B over 2r. And now there's nothing special about having started with vertex A for my diameter. I could do it through vertex B or C, and I would get the same thing 3 times. The opposite side over the diameter is the sine of the angle I started with. So the sine of A would be A over the diameter, and the sine of C would be C over the diameter. And then solving for the diameter, I would get the famous result. And speaking in the language of variance and invariance that I introduced for Taylor's theorem, this says that the ratio of a triangle's side to the sine of its opposite angle is invariant for a triangle, and it's equal to the diameter of the triangle's circumcircle, which is this extended version of the sine rule. Is a really nice way to see what this quantity means for a triangle. And it's actually, it's deduced in the first pages of this wonderful book, Geometry Revisited by Coxeter and Kreitzer. But it also gives us more about the geometry and trigonometry connection. Because imagine you have a triangle and you've constructed its circumcircle. All circles are similar, and therefore if you dilate the circle so that the diameter of your circle is 1, you have one of the most beautiful results in mathematics, I think. So we dilate our circle, so we have a unit diameter. That means twice the radius is equal to 1. We write out the extended sine rule and set 2r to 1. From that, we get 3 equations, solve each one for each length of the triangle, and you find that each length of the triangle is equal to the sine of the opposite angle in the unit diameter circle. I'll be using this result again later. So I've shown you the inscribed angle theorem and how it yields Taylor's theorem, and together how we can use them to deduce an extended version of the sine rule. And now I'll introduce you to Ptolemy's theorem. Ptolemy's theorem is about a quadrilateral that can be inscribed in a circle, and such quadrilaterals are called cyclic. So I have quadrilateral PIKA inscribed in a circle. Ptolemy's theorem says that the sum of the products of the opposite sides is equal to the product of the diagonals. So I've denoted a pair of opposite sides by green and the other pair in yellow. And so the product of IK and PA added to the product of IP and KA should equal the product of the two diagonals, KP multiplied by IA. And I've written the corresponding formula here for you. Now, you might have noticed that we've had an angle cat and we've had an angle quote, a Russian male cat. And so what is a pica? A pica is an alpine lagomorph. That's a mountain critter in the rabbit family. And they live at high elevations in some mountain ranges, such as the Sierra Nevadas, where I took this picture of a pica around 11,000 feet in elevation in Sequoia National Park. Okay, so how do we prove Ptolemy's theorem? In fact, if I go back actually a slide, how do you prove a theorem about products in geometry? How do you make a product? Start with similar triangles, write corresponding ratios, multiply through by denominators, I apologize, denominators, and that will give you a product. How do you create a sum? To create a sum, you break up a length into two lengths. So for example, I could put a point on IA in this diagram and then express IA as the sum of I to the point plus the point to A. So that's the strategy of this proof. First, I'll note that in this cyclic quadrilateral, angles KIA and KPA intercept the same arc. And so by the inscribed angle theorem, they're both half of the same thing, so they're congruent. Next, to make similar triangles, I'll create a pair of angles that are congruent. And at the same time, I'll create the sum that I need later. The sum IS plus SA will be equal to IA. So I've constructed KS so that angle IKS is congruent to angle AKP. And that gives me the purple triangle IKS and the green triangle PKA are similar because they share these two pairs of corresponding congruent angles, and therefore their third pair as well. By the similarity of those two triangles, I can write corresponding ratios. IS to IK in the purple triangle is the same as PA to PK in the green triangle. And then multiplying through by denominators, I can get a product. We'll call that equation 1. Now, in addition, there's more with similarity here, and as you can see, there are all sorts of inscribed angles and intercepted arcs. So if you look at these triangles, IKP in gold and SKA in blue, they both have an arc there, IK, with a corresponding inscribed angle. So that means that the angles, the inscribed angles I've indicated are intercepted by the same arc and thus congruent. And then both the gold and the blue triangles as well share a second pair of congruent angles. And that's because they have the one tick mark green angle that I constructed plus the shared angle SKP. And so therefore these two triangles are similar. Right there, corresponding ratios, IP to PK is equal to SA divided by AK, multiply through by denominators, and you get a second product. I'm running out of room on my slide, so I'm going to leave the rest of the proof to you, but here's the strategy. Add up equations 1 and 2, replace the length IA by the sum of the lengths IS plus SA, and then the result from Ptolemy's theorem, the sum of the products of the opposite sides is equal to the product of the diagonals, follows. So that's my hint for you to finish it. Okay, so I've shown you the inscribed angle theorem and a bit of this beautiful web of connection and Ptolemy's theorem. And now I think a highlight of this talk is going to be this lovely, surprising, and simple proof of the theorem of Pythagoras that drops right out of Ptolemy's theorem. I think you'll be delighted by this. So the strategy will be, I will take a right-angled triangle. Every right-angled triangle can be reflected so that it forms a rectangle. Every rectangle is a cyclic quadrilateral. Ptolemy's theorem applies to cyclic quadrilaterals, so apply Ptolemy's theorem and it will pop right out. So here is the rectangle inscribed in the circle. And then I'll apply Ptolemy's theorem, and that's it. That's the proof. So here I start with one of these right-angled triangles with lengths A, B, and hypotenuse C. Of course, since we have a rectangle, the other lengths are also A, B, and C. We need the 6 lengths from Ptolemy's theorem. So we have IK times PA. That's going to be A times A. Plus we have IP multiplied by KA, which will be B times B, and that equals the product of the diagonals, C times C. And so that gives you the famous equation that you all know and love. And I think that your students will be as delighted by this as you are. And I think that it's worth thinking about, thinking that some of our students should see this proof. Okay, so we have seen the theorem of Pythagoras, and now I think we're going to put together lots of these ideas to prove one of the trigonometric angle sum identities. Let's see which one. The sine angle sum identity. Okay. So here I have, here's the strategy here. I'm going to take a cyclic quadrilateral, and then I'm going to scale my circle, since all circles are similar, so that the diameter is 1 unit, which I have on the top. Twice the radius is 1, and rotate it around so that one of the diagonals passes through the center of my circle. And then I have the sine rule's consequences for the unit diameter circle up, because we'll be using them. What is the reason that I've rotated in such a way to get a diagonal through the center? That's so that I can apply Taylor's theorem, because I have a diameter, through the center. I have 2 angles inscribed in a semicircle, BAD and BCD, and therefore they're right angles. Now I'll take my angles alpha and beta, and I'll create an angle alpha plus beta, which is angle ABC. What we will do is slowly build up the 6 lengths from Ptolemy's theorem and then throw them together, and out will pop the sine angle sum identity. Consider triangle ABC. It is a triangle inscribed in a unit diameter circle, and therefore the sine of an angle is equal to, therefore, the sine of an angle is equal to the length of the opposite side by the sine rule. So that means that this length is sine of alpha plus beta. Consider triangle BCD. It is also a triangle inscribed in a unit diameter circle, and therefore the side CD is equal to the sine of the opposite angle, alpha, by the sine rule in a unit diameter circle. Moreover, this blue triangle is a right-angled triangle with unit hypotenuse, and that means that the side adjacent to angle alpha is the cosine of alpha. And now we're building up those lengths from Ptolemy's theorem. And what else can we find? The purple triangle. Triangle BAD is a triangle inscribed in a unit diameter circle, and therefore the side opposite angle beta is the sine of beta. It's also a right-angled triangle with unit hypotenuse, and therefore side AB is the cosine of beta. And now actually I have all 6 lengths because I've made this circle, constructed it, such that the diameter is 1 unit. Now I apply Ptolemy's theorem. I take the sum of the products of the opposite sides. So that's going to be purple times blue plus blue times purple. And then that equals the product of the diagonals, purple times gray. And so if we look AB, that's the cosine of beta, multiplied by DC is the sine of alpha, plus BC, that's the cosine of alpha, multiplied by AD, that's the sine of beta. And then that will equal BD, 1, multiplied by what we want, the sine of alpha plus beta. You can rearrange this to put it in the form you know and love, and there you have the sine-angle sum identity. I think I will kind of wave my hands and claim that if you know this identity, you can deduce the sine difference identity and the cosine sum and difference as well. In fact, all you need is 1 to get all 4 because of various trigonometric identities and the fact that the sine is an odd function and the cosine is an even function. And these are actually the 3 that I used on my scribbles to get the other 3 identities. And so I just chose the diagram that I like the best. After Chris Pritchard's talk, I think the importance of a beautiful diagram. There exist other diagrams to get the others. In fact, one of them is in this book, Trigonometric Delights by Eli Maurer. But I think the one I did is the one I like best. Okay, so now we have the cosine rule. And it's interesting to think about the theorem of Pythagoras as a special case of Ptolemy's theorem for an inscribed rectangle. We know that the theorem of Pythagoras is a special case of the cosine rule, which applies to all triangles for a right-angled triangle. So maybe it's not a surprise that it also pops out of Ptolemy's theorem. Let me first talk about why I've written the cosine rule in this form. I like to emphasize its connection to the theorem of Pythagoras, or in particular that it's just a special case. So when we have a right-angled triangle, we have a cosine of 90 is 0, and so a squared plus b squared is equal to c squared with no adjustment factor. When we have an acute triangle, a squared plus b squared, my hands are the same length, but c squared is now smaller. So we need to subtract something to make the quantities equal. And the cosine of an acute angle is positive. And now if we have an obtuse triangle, my hands are still the same length. A squared plus b squared is the same, but now c squared is larger. So we have to add something or subtract the opposite of something. And the cosine is negative for obtuse angles. So I like to think of the cosine rule as the theorem of Pythagoras with an adjustment factor that's a function of the cosine to work for all triangles. So what's the strategy for proving the cosine rule from Ptolemy's theorem? That is, start with the triangle, inscribe it in a circle. I've labeled sides A, B, C, and theta. Augment the triangle to form an isosceles trapezium, and then construct a rectangle. Since we have a rectangle here, this length is A, and so the 2 little bits that I added to form the rectangle at the top are both b times the cosine of theta, and there's 2 of them. And so that's a minus 2b cosine theta. So now is your turn to prove the cosine rule. You have the 6 lengths from Ptolemy's theorem, and then you throw them into the equation, product of one pair of opposite sides this geometry is hard for me. There we go. The product plus the product of the other pair of opposite sides is equal to the product of the diagonals. And there you have the cosine rule. So this is a beautiful, deep, wonderful web of mathematics. And it's really the inscribed angle theorem that puts it all together. And this is a theorem that I think that's clearly fruitful, and I'm going to try to argue is also surprising and overlooked and really important. So what I'd like to do is share why I think it's surprising, and then talk about some ways that I use it in my teaching and share some of that. So first of all, there's the proof diagram. And why is it surprising? Well, when I work with young high school students who are first engaging with this theorem, they tend not to think it's obvious, the result. They tend not to know the result. They tend not to figure it out immediately. They are not always convinced there is a relationship that's the same for each inscribed angle and corresponding arc. And when I work with students who know the result, they often don't know why. So to me, those are suggestions that if we look at this theorem with new eyes from the web that comes from it, and as young learners seeing it for the first time, it's a surprising theorem. So my suggestion and what I like to do and has worked in my classroom is to let students explore the relationship first. Either pose the question, or ideally what I try to do, which doesn't always work, is to get students to come up with the questions themselves before they're presented with the result, which is the answer to the question which often they've never asked themselves. So give students the space and time to explore the relationships first between an inscribed angle, a central angle, an arc, a chord for a given circle. After they've had time to do that, they can make conjectures, and some of their conjectures may be correct, and some may be incorrect, and some may be correct in different cases. And if you remember back to last year's keynote address by Craig Barton, there were some really lovely suggestions for teaching the notion of an angle, how to measure an angle, what it means. And I think that the inscribed angle theorem is another good context for teaching students how to measure with the protractor, because it gives them a context or a reason to want to measure. And I think you can do this in pure mathematics context like this, but also in applied context as well, giving students some question that requires them to measure with an angle, and then teaching them the skill that they need. What's really fun is when students pool together their data for many different angles and inscribed angles, you can motivate the measures of dispersion that we teach, like the standard deviation and the interquartile range and the range, as well as measures of central tendency like the mean and the median, through students discussing the data that they get. And our students can come up with these ideas, certainly of the range and the mean and the median, and even the average difference from the mean. My students have come up with this idea, and then we can give them a name for this. And so it can emerge naturally from our students playing with the inscribed angle theorem's data. I think it's really important that this is a gentle and relatively simple proof for this theorem, that students who are working with isosceles triangles and circles and the triangle sum theorem can understand and work with the teacher and work together to come up with a proof. Many of our students never see proof because it's only formally in advanced higher. And so opportunities to connect the web of knowledge, of mathematics, and to develop proof earlier, I highly recommend. Also, I recommend opportunities for working with great mathematical texts. Mathematics is a subject that has great mathematical texts. Not only is this theorem from Euclid's Elements, but also, and as Chris Pritchard also showed in his talk, There's a lovely 1847 visual version by Oliver Byrne of the first 6 books of Euclid's Elements. I'm showing you the 2013 facsimile edition, and here is the page of the Inscribed Angle Theorem, Proposition 20, Book 3. It's very rewarding to work with students with great texts. Those texts also are not always what we think they are. There are lots of claims we make about these texts, and I've always found that the statements of the theorems, including the one I've given you today from Euclid, are slightly different than the way that we've stated them. And as an added bonus, we can use Ptolemy's theorem to deduce that the ratio of the lengths of the diagonal of a regular pentagon to its length is the golden ratio. So you may know this result. If I take a regular pentagon and I take one of its diagonals of length x, and I call its side length 1, then the ratio x to 1, the diagonal to the side length, is equal to 1 plus the square root of 5 over 2, the golden ratio. And you can prove this with Ptolemy's theorem. Here we have our cyclic quadrilateral. Sorry, I'm using my finger and it's not as good as the pen I usually use. So, and then I have the 2 diagonals from this regular pentagon there. Each of the side lengths is 1. Each of the diagonal lengths is x. So the sum of the products of the opposite sides, 1 plus x, is equal to the product of the diagonals, x squared. And you might recognize that the positive solution to that quadratic equation is the golden ratio, 1 plus the square root of 5 over 2. And so that is the ratio of the diagonal's length to a side's length in a regular pentagon. In fact, you can see this green similar regular pentagon, and this is actually a way that you can prove that the square root of 5 is irrational. I know that the square root of 2 is irrational as a common proof in advanced higher, but imagine that the square root of 5 is rational. Then 1 plus this rational number over 2 would be rational, and the golden ratio would be rational. And so the ratio of the diagonal to the side of a regular pentagon would be rational. Say the number a over b. If we're in lowest form, if we're fully simplified, we multiply through by b, and we get an integer-sided, integer-diagonal pentagon, regular pentagon. And that will be the minimal such one. But there's the green one in the middle there, which is similar. It has the same ratios. So that violates the assumption of minimality, and therefore there is no such integer minimal regular pentagon, and the square root of 5 and thus the golden ratio are irrational. So I'm going to stop and thank you. Before questions, I'll spend the last 7, 8 minutes if you have questions. Here's the web of mathematics that comes from the Inscribed Angle Theorem. There's my email address if you want to contact me. And I'd like to acknowledge Dr. Clara Cohen for her help with my figures in this presentation and for tech support. And I'd like to acknowledge Mrs. Lucy Anderson for helpful feedback from an earlier version of this talk. So I'd like to take questions.